to illustrate a couple of things. One, I want to talk about the complexity of some of the food systems that we work with. And as I go through my presentation today, I'll be kind of pointing out some of the unique kind of product package interactions. I'll also touch upon some of the dough chemistry questions that were brought up earlier with regard to the importance of leavening systems and reaction kinetics and the such like. I'd also like to share a quick story. Refrigerated dough is quite unique, and it was actually developed by a gentleman called Lively Willoughby. That was his actual name, Lively Willoughby, in 1931 with the Ballard Biscuit Company out of Louisville, Kentucky. And he had a very interesting past. I think he was a circus performer and a few other things too. But we have Lively to thank for that very unique product system. By way of introduction, my name is Dave Domingues. I am a fellow with General Mills. I work in the Refrigerated Dough Division Technology Group. Let's see here. I think I have a clicker. All right, let's see if I get this right. Hold it the right way. All right, there you go. We'll see. All right. Well, let's talk about refrigerated dough in general. It's a big business for us. General Mills net sales is about $19.2 billion a year, of which 10% is dough. So just a little under $2 billion in dough, of which $1.3 billion is refrigerated dough. And so the specific case study I'm going to talk to you today about is specifically pressurized canned refrigerated dough. And I'm going to touch upon some case study kind of work about some of the challenges of sodium reduction and also some of the microbiological interactions. So first, let's talk about what refrigerated dough is, because it is unique. Start off with, we have a spiral wound cardboard can. I guess most of you have tried these products before. You may raise a hand if you crescent rolls at Thanksgiving time, maybe sweet roll. All right. So you start off with a can into which we insert dough. And here I've got an example of biscuit pucks being inserted. And I could spend time just kind of showing you video of how this is done in a manufacturing setting, because it's really quite amazing the speeds at which we operate at. What happens next is that we have chemical leavening in these systems. We're going to get into that. Basically, phosphate leavening acids and soda. All right, sorry. Got to talk into the microphone. And the dough starts to expand in the can. And the metal end lid is actually sealed on, but it's not a hermetic seal yet. What happens as the dough expands is that it forces air out of the can through these vents along the seam of the end lid. And with time, usually depending on where the dough is located within the pallet, usually within hours, although in some instances if the dough gets very cool, it could be within a few days, the can will pressurize to about 14 to 17 pounds per square inch. And it's an anaerobic environment. Now this is very important because in the video that you saw when she wrapped, and we don't recommend you do that, by the way, anymore. We recommend that you unpeel it and then use a spoon to open the can as you take it out and wrap it against the counter. So you saw the dough expanded. That expansion is a very important functional piece of how this product operates, because it's the initial density of the dough when you put it in the oven that's related to the final volume when it bakes up. And also there are some safety concerns, of course, because we've got a pressurized vessel here. And we designed the end lid, it's seamed on, such that when it reaches, depending on the product system, anywhere from 24 to 25 pounds per square inch up to maybe 30 pounds per square inch, it will explode, or not explode, but fail. Don't like to use that word. All right, well, let's talk about where the sodium comes from. All right, let's see here. I guess the laser pointer is here with a little red dot. All right. About 39% comes from sodium chloride, and almost a little over half actually comes from the leavening system. Our leavening system is sodium acid pyrophosphate, sodium aluminum phosphate, and sodium bicarbonate. And you can think of that as kind of baking powder, you know, that you would kind of buy off the shelf. So you can see that our challenge really, we can reduce the sodium, but we still have this leavening piece to kind of work with. Oops, sorry. Let's see if I can. All right. I hit the wrong button. There we go. All right. All right, let's talk a little bit about leavening chemistry. And basically, it's a neutralization reaction. Here's our acid. This could be phosphoric acid, or in some instances, an organic acid, such as tartaric acid or lactic acid. Here's our sodium bicarbonate, and with moisture and heat, we get the conjugate base, a little water released, and then carbonic acid, which can dissociate into carbon dioxide. The rate of this reaction, you heard several speakers talk before, is critical to dough manufacturing. If it goes too fast, the dough actually will expand on our manufacturing lines, and we can't cut it and get into the cans. If it goes too slow, it won't proof the cans up in time. And if it doesn't proof the cans in time, and we have air pockets within the can, we have quality issues. Wheat flour is not pasteurized, has a lot of native enzymes, specifically polyphenol oxidase, which in turn can turn the dough gray, and you get this kind of discoloration. So it's important that that proofing that I demonstrated earlier happens within a specific period of time. Also, and we're going to get into some of the chemistry here, the rate of the reaction is also a function of the dissolved ions. And so when we start talking about reducing sodium, we're affecting the ionic strength of the aqueous medium of the dough, which in turn affects the dissociation of these acids. Some of the reduction strategies which have been mentioned before are using what we call non-sodium salt analogs, potassium bicarbonate, the calcium acid pyrophosphate, and organic acids mentioned earlier. So we first tried just reducing sodium in the can. So we said, well, let's just take sodium out, kind of reduce it down. And this is what we found. On the y-axis is can pressure in pounds per square inch, and the x-axis is percent sodium. And as we reduced sodium, we found that our can pressures were significantly less. And we'll get into it. This is due to Le Chatelier's principle, or the law of calibration. And we had a program that we participate in. It's the MIT Practice School. We spend 6 months working with graduate students at MIT in chemical engineering. And we actually kind of worked out the chemistry and the dissociation constants and developed a model to predict can pressure as a function of ion concentration and temperature and leavening amount. But just to simplify it, here we have our phosphoric acid, and you have a couple of dissociations. And what happens is that when you have salt in your system, the salt can form a conjugate base, which in turn drives the action forward, and we kind of react more completely, and we get higher can pressures. So when we took the sodium out, we weren't forming these conjugate bases anymore. Moreover, as we change the nature of the ions that are there, the rates of these other reactions change also. So if we go to a magnesium salt, we were using a carnallite salt from Dead Sea salts, we found these reactions were accelerated significantly. We couldn't get the dough in the can. It was just expanding before your eyes. And again, that's because the conjugate base formed with the magnesium happens so quickly. Let's talk a little bit about microbiology and water activity and can pressure. I mentioned earlier that refrigerated dough is made with flour. Flour, of course, has its own microflora that comes with it out of the plants, specifically lactic acid bacteria. And, of course, the lactic acid bacteria, under the right conditions, will produce lactic acid, which in turn lowers dough pH. Now, their growth is a function of water activity, temperature. And so as we reduce the salt, we increase the water activity, and the lactics can grow and depress pH. And so I have one plot of data down here showing dough pH versus log lactics. And you can see here, once we got to about 10 to the 6th, the pH decreased quite readily. Why is this important? It's important because of this relationship here. What we have here is the bicarbonate here, and then here we have carbonic acid. Here's pH, and you can see dough pH is right around here, just slightly acidic. So slight changes in pH of the dough can greatly affect the concentrations of these two different species. Of course, the carbonic acid can dissociate into CO2 and water. And what happens is when the lactics grow and produce acid, we form the carbonic acid form, which dissociates, and our can pressures increase, and we end up with can failure. And I would argue that probably a majority of our can failures that aren't related to malfunctions and seaming or can defects are related to microbiological activity. So just to kind of graphically point out what can happen is that over time, higher temperatures, lactic growth, pH decline, CO2 production, and can burst. And so we do a lot of work trying to control water activity, and if we start reducing the sodium, then we have to take a look at other materials. You can look at your sugar alcohols, you can add your sugars, but those carry organoleptic kind of baggage. In addition, they're not as effective. Salt's a very small, highly charged molecule, and it's very, very effective at reducing water activity. So water activity bang for your buck, you really can't beat kind of ionic salts. And of course, it affects flavor, which many speakers prior to me have mentioned. So the challenge again are the ions and the dissociation of the phosphoric acid. And again, we have to have specific critical reaction rates. We need the dough to be dense enough that we can manipulate it and sheet it and get it into the can and then have it proof. Other speakers have already talked about dough development and rheology, and you can imagine if you've ever been to a refrigerated dough processing facility, the speed at which we run our lines is incredible. It's not the mom and pop bakery. You know, we've got thousands of pounds of dough kind of whistling by like a freeway. And so rheological changes in the dough are very critical. And you mentioned sorbic acid earlier. We have sorbic acid as a processing aid, helps relax the dough, makes it more like taffy. You can kind of stretch it out and enables you to kind of run and process it more efficiently. So we spend a lot of time understanding and characterizing. In addition, I should mention, wheat flour is a crop. Every year it changes, all right? So you have the crop year changeover. You know what? It's a headache. We all come into the plant and we're trying to characterize it. And the dough and the proteins, I think Janice from Cargill mentioned, they change. And so we sit down and we spend a lot of time waiting for the flour to mature and the relationship of the gluten to kind of change. And it's always an exciting time for us with crop year changeover. Again, we have to find means of trying to reduce water activity or maintaining water activity. And I should mention, I didn't put any numbers up. Dough generally is about 0.92 to 0.93 is kind of where we try to target. It can get as low as 0.91 in some of our cinnamon roll filling systems, but that's generally kind of where we're at. In addition, because we do have the lactics, they are kind of a safety mechanism, so if the product is abused and for whatever reason we don't hit the water activity targets, the cans will kind of increase in pressure and burst before there's a chance for any kind of pathogen growth. There are still the same limits everyone else has, and we've employed the same strategies other folks do. We don't replace all the salt, we replace part of the salt with potassium chloride. And of course, we use it on a molar basis. I think we were talking earlier, we always talk about molality with regard to the salts that we use, and not just simply kind of a weight for weight kind of change. And we do have issues with some people being very sensitive to this metallic or bitter, or I think Paul mentioned spar. I like that flavor. All right. So, kind of whip through these pretty quickly. We'll have plenty of time for questions. I'm going to talk a little bit about spoilage and waste, and I thought I'd maybe just kind of go over some of the numbers, and then we can have some times for some questions, and I think we have a panel, or actually we have a break afterwards, so maybe we have just an extra long break. So overall, our unsaleables are about just a little bit below, I was going to say 2%, 1.88% of our gross sales are unsellable, of which 86% actually is due to out of date. And the nature of our business is a forecasting business. We have to forecast how much, and we set our production schedules up. And so it's about rotation at the shelf. That's a big issue for us. And so when our products are out of date, we have to pull them off. And we've been working on kind of new dispensers in order to enable the older product to go first, as opposed to having consumers come and kind of cherry pick and then the old stuff gets left behind. About 14% of that 1.88% is due to damage, and this can be anything from warehousing, kind of handling, moving pallets around. So we do a lot of work on reconfiguring pallets and to ensure that products aren't damaged, and also premature can failures that might occur at the retailer. And in turn, we budget for this, and so what happens is that this product then goes to a reclaim center, and we get a bill for it. Now, of course, the customer has already purchased the product, and then we just buy it back, the unsaleable portion of that. And what the product that goes typically goes to a landfill. So clearly we're interested in trying to reduce these numbers and reduce the load on the landfill. Factors to consider with waste and spoilage. Again, our business is seasonal. We have a very large demand in the fall, which we call our baking season. So it's a big deal for us. We sell like 90% of our pie crust in October and November. That's right. So we make it and we kind of freeze it and then we slog it out, but we just run that line and then we're kind of done with it. And then of course the biscuits and the crescents for all the holiday meals that occur. Not as bad as, I always kind of wondered, about other industries like, the Easter egg dye company, Can you imagine when Easter rolls around for them? They're like, okay, this is it. This is our Super Bowl. Everyone, what's the new color this year? All right. Product is produced to forecast. I mentioned that earlier. We have a very complex channel. There are 22,000 retail outlets. And I should mention about a third of the shelf life of the product, which, by the way, is approximately 90 days, refrigerated, is in distribution for just getting it from A to B. We spend up to almost a month getting the product from our distribution centers to other substations and then out to the retailer. We have looked at other means of leavening dough before. I don't have a slide prepared for it, but CO2 is a very soluble gas, and we've kind of looked at actually kind of flushing dough systems without leavening with CO2 gas in order to expand the volume. So that's one strategy that we have explored before. We've looked at also, again, looking at the more traditional forms of leavening. I mentioned earlier, buttermilk has a lot of lactic acid in it, and we've looked at using buttermilk solids, and also cream of tartar to taric acid historically had been used as an acidulant, but they're organic acids, they're very soluble, they're difficult to control the rate. Remember I mentioned earlier how important that is, and so usually it has to be used in combination with encapsulation or some other means of mitigating reaction rates. So it's fascinating to see what people do for a living, and hopefully you've learned something that you didn't know about refrigerated dough today, so you won't look at the dairy case the same way as you come along. And I think the last thing, I shamelessly put another doughboy up there. And oh, by the way, I do have something for Delia for doing such a wonderful job organizing this. I've got a doughboy. There you go.